So, welcome to the 5th lecture of probability, dear students. And I start as usually by recalling what we did last time. So, last 2 weeks, we worked with so-called random variables. And random variable x is mapping from the set of elementary events to real numbers. We start with some description of random variables. Where we said that the general description of a random variable is so-called cumulative distribution function, which is a function f of real variable u, given by the description that it is the probability that x is less or equal to u for all real numbers u, or another description which depends on the type of random variable. And we said that for discrete random variables, we can use more natural description, probability that x is equal to k for all taken values k. Again, they are from R, but usually we care about some numbers of events and so on. So usually k is a natural number. But in general, it can be an arbitrary real number. The point is that there must be finite or countably infinite number of values which are taken. Or for continuous, random variable, we use function fx called probability density, describing how the probability is distributed in taken values, but the number of taken values can be uncountably infinite. So there, it can be continuous on the real x, therefore also the random variable is called continuous. And the probability density is the analogy of probability in the first case. So the total amount of the probability must be equal to 1. So the integral of the density from minus infinity to plus infinity must be equal to 1. And today I will show you some examples, some basic models of these discrete and continuous random variables. As I said, there can be also their combination, but we won't care in this course of these combinations. We will work only with discrete or either discrete or continuous random variables. So today I will show you some examples. Last time I showed you how to calculate some basic characteristics. And the basic characteristics which I mentioned were the following. First, it was the expected value, which is either a sum of the taken values multiplied by their probabilities, or analogously an integral from minus infinity to plus infinity from x times density of x dx. For continuous random variable. And we said that it is an analogy of the average Then the second characteristic which I mentioned here was the variance of x, and the variance of x is the expected value, so the mean value, the average value of the square distance of the random number, random variable from its expected value. And I show you that it can be calculated as the expected value of the square of random variable minus the square of its expected value. I explain you the difference between the expected value of square and the square of expected value. So everything what is written here was done in the last 2 weeks. And as I promised you, I will show you some basic models, some basic cases of discrete and continuous random variable which you can use in practice. So we'll start with discrete. Random variables. And as usually, I will start with an example. Consider our favorite example that we throw die, and x is the random variable, the random number describing the number of successes where success means that there are 6 spots on the die in one trial. I mentioned this last week, but I recall that when we consider one trial and we calculate the number of successes, then there can be either 1 or 0 successes. And when we throw a die, classical die, then there is probability 1/6 that there will be 6 spots on the die. So the probability of success, of one success, is 1/6. And the remaining probability, 5/6, belongs to the situation that the number of successes is equal to 0. In this case, we say that X has alternative distribution with the parameter 1/6. Or sometimes it is called also Bernoulli distribution with the parameter 1/6. Yes, so we read this formula as X has the alternative or Bernoulli distribution. What does it mean that X has the distribution? The distribution, from a mathematical point of view, is that it is a probability measure which is some function with some special properties and so on. But practically, we can imagine the term distribution as the way how to distribute the total probability it means the number 1 among the taken values. And so for us, it means that it is the description how to distribute the probability 1, the total amount of probability, among the values which can be taken. So in our case, only the numbers 1 and 0 can be taken. So we distributed the probability 1 so that to the value 1, the probability 1/6 was given, and the remaining probability 5/6 was given to the taken value 0. Yeah? And what about the characteristics of this random variable? Expected value is the sum of the taken values multiplied by their probability. So in our case, it is 1/6. The variance is the expected value of x squared minus the square of expected value, and the expected value of x squared is given by the squares of taken values multiplied by the probabilities of the taken values. So it is 1/6 in our case, and so the variance is 1/6 times 1/6, sorry, minus 1/6 square. So we can write it in this form. And we can see that in fact the variance is equal to the probability of success times the probability of failure. So in general, when we care about something else, but we still observe or we still model the number of successes in one trial, so it means either success or failure. And the probability of success is given by a value small p. Then we say that the random number, the random variable, has alternative or Bernoulli distribution with the parameter p. And of course, when the probability of success is equal to p, then the probability of failure, it means the probability of 0, is equal to 1 minus p. The expected value in our case is equal to 1/6, which is the probability of success, and it holds in general. You can try to prove it. It's a quite easy exercise. So in general, the expected value of x is equal to p, and the variance of x is equal to p times 1 minus p. So in fact, the probability of success times the probability of failure. And so this is the basic model of discrete random variables. We will use it in a more difficult situation, so you will meet this random number very, very often in this lecture. But it's, as I said, just help distribution. And when we calculate some practical examples, we need more sophisticated random variables. So now consider a situation that we threw a die, but not only once, but more times. Let's say no, 4 times. So 4 times we threw the die. And again, x denotes the number of successes. Now, we can have 0 successes, 1 success, 2 successes, and so on, times 3 successes and 4 successes. I will write all options. How will we distribute the probability among these 5 values? What is the probability that x is equal to 0? So it means that 0 times we threw the die and there were 6 spots on the die. It means that 4 times we had less than 6 spots on the die, the probability that in one trial there is less than 6 spots on the die is 5/6. So it must happen 4 times. When we care about the probability that the number of successes in 4 trials is equal to 1, it must happen that once we threw the die and there were 6 spots, times the probability of less than 6 spots powered by 3. But this is the probability that the 6 spots were in a concrete trial. For example, in the first trial. But there are more possibilities how to get one success in 4 trials. It can happen in the first trial that we have 6 spots on the die. It can happen in the second trial, in the third trial, and in the fourth trial. So there are 4 probabilities, 4 possibilities having the same probability. So the probability must be multiplied by 4. And what happens in the situation that we care about the probability of 2 successes? Twice it must happen that we have 6 spots on the die. Twice it must happen that we have less than 6 spots on the die. And what is the number of situations? So in fact, what is the number of couples of positions of successes? We have 4 trials and we care about 2 positions. So the number of couples of positions for 2 successes in these 4 trials is 4 choose 2. And the number of couples from 4 positions, from 4 elements. And in fact, we can maybe see some system in these probabilities, because this number 4 can be written as 4 choose 1. Similarly, in the first case, we can write the probability as 4 choose 0 times 1/6 powered by 0. And similarly, we can write 4 choose 3 times 1/6 powered by 3 times 5/6 powered by 1, the probability that the number of successes is equal to 3. And 4 choose 4 times 1/6 powered by 4 times 5/6 powered by 0. So we can briefly write only the description that the probability that x is equal to k is 4 choose k times 1/6 powered by k times 5/6 powered by 4 minus k for k equal to 0, 1, 2, 3, or 4. And this is the way how to distribute the total amount of probability 1 among the values, taken values 0, 1, 2, 3, 4. That's it. How can we prove that the sum is equal to 1? You can use the binomial theorem. And from this reason, this distribution is called the binomial distribution. It is denoted so that X has the distribution, and this wave means it has distribution binomial, and it is given by two parameters, by two informations which we need to know. How many trials we have, and what is the probability of success in each trial. So in our case, X has binomial distribution with the parameters 4 and 1/6. In general, when we model the number of successes in n trials, and independent trials, it is also very important that the trials must be independent to each other. So when we care about the number of successes in n trials, we use this binomial distribution. And in general, we can have n trials. The probability of success in each trial is equal to p. And then the probability that x is equal to k for k from 0 to n is equal to n choose k times the probability powered by k times the probability of success powered by k times the probability of failure powered by n minus k. Yeah? And the reason was shown on this example. So this is the description, the way how to distribute the probability. And now, what about the characteristics? So you can calculate that expected value is equal to n times p, and the variance is equal to n times p times 1 minus p. But the calculation is quite crazy, as you can see here. So you can imagine it in other way. Imagine x. Imagine x in a special form. And the special form is that it is the sum from 1 to n of xi, where xi has alternative or Bernoulli distribution with the parameter p. Why can we write x in this form? Because you can imagine it in the way that xi is either 1 or 0 when we have success or failure, respectively. So it means that always when the ith trial we obtain success, we add 1. And so, for example, when we 4 times throw the die, it means that in the first trial we have the success. So we calculate 1. Plus, in the second trial, we get number 2 on the die. So it is failure, it is 0, plus 0. In the third trial, we again obtain 6 spots. So it is again success, and we add 1. And in the fourth trial, we have again, I don't know, the number 3. So it is the failure, number 0. So when we have xi to be equal to 1 when we have success in the ith trial, then the number of trials in n, number of successes in n trials is in fact the sum of these elementary successes in each trial. And then we know that the expected value of x which is the expected value of the sum of xi, is equal to the sum of expected values. Because expected value of sum of random variables is the sum of their expected values. The expected value of xi is equal to p. So in this way, we get n times p. And similarly, when we calculate the variance of x, it is the variance of the sum of xi. And in the list of properties of variance, you can find that the sum of random variables has the variances equal to the sum has the variance equal to the sum of variances plus minus some covariances, which are we will talk about it later, which are equal to 0 when these random variables, it means when the trials are independent. So thanks to this independence, we can write that it is the sum of the variances, and we know that the variance of a Bernoulli distributed random number is equal to p times 1 minus p. So the variance of x is equal to n times p times 1 minus p. So this is the way how to show quite easily the characteristics of random variable with binomial distribution. So it was the second example. And now I will show you maybe the most important distribution we will use in this course. I mean the most important discrete distribution. And I will show you also the connection to the previous distributions. So imagine the situation that x has binomial distribution with the parameters n and p. And imagine that n is too large and p is too small. For example, when you have some insurance, the insurance company has many contracts, and in the contract, when you imagine, for example, some car insurance, then in these many contracts, there is quite small probability that there will occur an accident. So it means that the insurance company will have to pay something to the person of the concrete contract. So it means that the probability that x is equal to k is n choose k times p powered by k times 1 minus p powered by n minus k, which is n times n minus 1 times and so on times n minus k plus 1 over k factorial. It is the way how to calculate the number n choose k. Times p powered by k times 1 minus p powered by k. Powered by n minus k. It is equal to, first, I will add you some notation. Expected value of x is equal to n times p. Let's denote it as lambda. We know that n goes to infinity and p goes to 0. But it goes to infinity and p goes to 0 in the way that still their product is equal to lambda. Then this product, when n goes to infinity, goes to n powered by k times p powered by k, which is lambda powered by k. This term is equal to 1 minus p powered by n times 1 minus p powered by minus k. And since p goes to 0, this term goes to 1. The most difficult situation is here. This is, in fact, 1 minus lambda over n powered by n. And if you remember, the limit of this term, it is e powered by minus lambda. Yeah? So it means that we can approximate the probability by lambda powered by k over k factorial times e powered by minus lambda. And in this way, we can distribute the probability 1 among the values 0, 1, 2, and so on to n, but n is too large and goes to infinity. So, in fact, in the situation when n is as large that it can be considered to be equal to 0 and p is very, very small, then the probability that there will occur k successes, if we can call the accident to be the success, so let's say the number of events equal to k, the probability that the number of events is equal to k can be calculated by this description. We will use it in other situations, and these situations, yeah, I have some space there, so I will write it here. We will use it in the situation where x denotes the number of events in usually in some time interval, but it can be also used for calculation of the number of some events in an area, and so on. You will see later an exercise and other examples. But Imagine now that here we have some time interval. And we divide this time interval to many, many small times intervals. Such that in each interval there can occur at most one event. Yeah? So the intervals are so small, so short. In fact, I mean, in the limit, it is equal to 0, but we cannot consider exactly 0. So we consider so small intervals that in each interval, either 1 or 0 events occur. And it means that xi is the number of events in the ith interval. So it means that xi has alternative or Bernoulli distribution with the parameter p, and it means that when we calculate the number of events in all in the whole interval, then x has binomial distribution with the parameters n and p, but n goes to infinity and p goes to 0. And so in fact we have infinite number of these intervals, infinite number of trials, and some small probability of success of the event in each trial. So we will use the approximation that probability that x is equal to k is equal to lambda powered by k over k factorial times e powered by minus lambda for k equal to 0, 1, and so on till infinity. And this approximation is called Poisson distribution. We write it again briefly that x has the distribution Poisson, and it is given by only one parameter lambda. And how to calculate the examples in practice? When we calculate the examples in practice, this lambda is the most important term. In fact, it is the only important number which we need to know. And when we go back to the beginning, we know that lambda is equal to expected value. So in this case, the expected value, which is, as I said, an analogy of average, is very important. I will show you a concrete example immediately. So, the number of some events, so something more practical. The number of clients coming to a shop or coming to a bank is 3 per hour in average. And this is very important. What is the probability that there will come at least 2 clients in the following half an hour. So, how to solve such an example? First, we must define our random number we will work with. So, x, the random number, will be, of course, the number of clients. Now we must specify the time interval we care about. And because we ask what is the probability there is at least there will come at least 2 clients in the following half an hour, we will care about this half an hour. Or 30 minutes, if you want. The number of clients is the number of events which come independently to each other. So it is the number of independent events in some time interval. And it is the situation when we use the Boston distribution of probability. Now we must find lambda. Lambda is the average, the expected value or the mean value, and the mean value means, in fact, the average value, theoretical average value. We know that in average there will come 3 clients per hour. So it means that for half an hour, the average number of clients is 1.5. 1.5 is half from these 3 clients. It is the average, so we don't care that it is decimal number. It is the average, and when we have 3 clients per hour in average, it means that per half an hour we have in average 1.5 clients. So it means that, or maybe it's better to write that, it means that the probability that exactly k clients will come in the following half an hour is equal to 1.5 powered by k over k factorial times e powered by 1.5 for k equal to 0, 1, and so on. So the probability 1 is distributed among the values 0, 1, 2, 3, and so on till infinity in this way. Each k is given the probability 1.5 powered by k over k factorial times e powered by minus 1.5. And we ask, what is the probability that at least 2 clients will come? So it means that the number of clients in the following half an hour is at least 2, greater or equal to 2. It is easier for us to calculate this probability as 1 minus the probability that the number of clients is less than 2, which is 1 minus the probability that the number of clients is equal, less or equal to 1, because it is 1 minus the probability that the number of clients is equal to 0 plus the probability that the number of clients is equal to 1. And for these probabilities, we know the description. So it is 1 minus the probability that no client will come in the following half an hour is 1.5 powered by 0 over 0 factorial. 0 factorial is equal to 1, by the way, if you forget. And it is multiplied by e powered by minus 1.5. The probability that exactly 1 client will come in the following half an hour is equal to 1.5 powered by 1 over 1 factorial times e powered by 1.5. Yeah? And it is, if you want to have it in some nice form, so 1.5 powered by 0 is 1, over 1 is 1. This is 1.5, so 1 minus 2.5 times e powered by minus 1.5, but it is not important. The result is written, the main result is written here. When you use, I will repeat it once again, this approach. The probability that x is greater or equal to 2 is 1 minus the probability of complementary event that x is less than 2. When we care about the number of clients, x is less than 2 means that x is at most 1. And the probability that x is at most 1 is the probability that x is equal to 0 plus the probability that x is equal to 1. And for these probabilities, we know the description. Yeah? So that's the way how to work with so-called Poisson distribution. I will show you one more example concerning the same situations, the same situation with the clients in the bank. And we can transform this example in the following way. What is the probability that between 8 a.m. and 10 a.m. there will come at most 4 clients, while all these clients come after 8:30. So in effect, we have two tasks. What is the probability that in 2 hours there will come at most 4 clients, and that all of them will come after 8:30? Maybe you want to solve it as a random number concerning the number of clients in these 2 hours, and then to add somehow the condition what happened before 8:30 and after 8:30. But here we should use the information that the Poisson distribution is used for the number of events which are independent to each other. Yeah? And when we have independent events, A and B, then we know that probability that both of them occur can be calculated as the product of their probabilities. So also in this case, we can work with some independent events. And the independent events are the number of clients, and that there will be a concrete number of clients in independent time intervals. So it means that here we denote X the number of clients between 8 and 8:30, and the number of clients between 8:30 and 10. Because when we want all these clients to come after 8:30, then they cannot come between 8 and 8:30. And so we care about these events separately. And both of these numbers are the numbers of independent events. So X and Y both have Poisson distribution, and the parameters are 1.5 for X because we again consider 30 minutes, and 4.5 for y, because we have 1.5 hour, and in the case that we have three clients per hour in average, then it means that in average in 1.5 hour we have 4.5 clients. So it means that probability that x is equal to k is as before 1.5 powered by k over k factorial times e powered by 1.5 for k equal to 0, 1, and so on. The probability that y is equal to L is 4.5 powered by L over L. L is not a good number. M powered by M over M factorial times E powered by minus 4.5 for M equal to 0, 1, and so on. And now we want to calculate the probability that nobody will come between 8 and 8:30, and then in the remaining time, at most 4 clients will come. Usually when we work with random variable, we don't write the sign for intersection, and we write only the comma, but it means the same. And so in the sequel, I will write comma instead of the sign for intersection, but I will mean the same. And these events are completely independent. So the probability of their intersection is the product of the probabilities of these events. Probability that x is equal to 0 is 1.5 powered by 0 over 0 factorial times e powered by 1.5. So it is the first probability times the sum of probabilities that y is equal to 0, y is equal to 1, y is equal to 2, and so on. So 4.5 powered by 0 over 0 factorial times e powered by 4.5 plus 4.5 powered by 1 over 1 factorial times e powered by 4.5. And this is the probability that y is equal to 0. This is the probability that y is equal to 1, plus, and so on, plus the last term is 4.5 powered by 4 over 4 factorial times e powered by 4.5, which corresponds to the probability that y is equal to 4. And this is the result. Probability that x is equal to 0 times everything what is in the brackets, meaning that y is at less or equal to 4. Yeah? And that's the result. So this is the way how to work with random number with so-called Poisson distribution. Yes, sir, I forgot to tell you how is it with characteristics. So we know that the expected value is equal to lambda. In fact, we use it as the basic tool for calculation of the examples. And the variance is also equal to lambda, which can be shown in quite easy calculation. So it is also your homework to try it. And now I would go to the fourth discrete distribution I want to show you. So, example. Let's go back to our situation that we threw our die and success means that we have 6 spots on the die. And we care about a random number describing the number of failures before the first success. So, how many failures can we have before the first success? Either 0, or 1, or 2, or infinite. What are the probabilities? The probability that there is 0 failures before the first success means that the success occurred in the first trial. And it means that in the first trial we got 6 spots on the die. The probability that there is 1 failure before the first success means that in the first trial we were not successful and in the second one we were successful. So there was 1 failure and 1 success. The probability that there are 2 failures before the first success means that first there must occur failure, then it must occur the failure again, and in the third trial we must be successful. Yeah? So in fact, it means that the probability that there are k failures before the first success is probability of failure powered by k times the probability of success, and this probability is distributed among the values 0, 1, 2, and so on till infinity. So when we want to calculate what is the probability that that there will be at most 5 failures before the first success is calculated as the probability that the number of failures is less or equal to 5, which is in fact the sum of probabilities that x is equal to 0, to 1, to 3, and so on to 5. It is the sum of 5/6 powered by k times 1/6. 1/6 doesn't depend on k, so we can write that it is 1/6 times the sum from 0 to 5, 5/6 powered by k. And probably you remember that this is a geometrical series, and when you have in general the probability, the sum of k from 0 to n, from q powered by k, absolute value of q is less than 1, but it must be in our case because we work with probabilities, then it is 1 minus q powered by n plus 1 over 1 minus q. So in our case, it means that it is 1/6 times 1 minus 5/6 powered by 6, 5 plus 1, over 1 minus 5/6. 1 minus 5/6 is 1/6. So 1/6 divided by 1/6 is equal to 1, and we obtain 1 minus 5/6 powered by 6. This is one way how to calculate the example of at most 5 failures before the first success. But it is not the only approach. Another approach use y the number of successes in 6 trials. Why? Because at most 5 failures before the first success means that we can have 5 failures, but in the 6th failure there must occur the success. And it means that why we care about the number of successes of 6 trials, y has binomial distribution with the parameters 6 and 1/6. 6 trials, 1/6 the probability of success in each trial. And at most 5 failures before the first success means that in the first 6 trials, there must be at least 1 success. Because if the success is in the first trial, it is okay. If the success is in the 2nd and in the 5th trial, it is okay. And so we don't care about the position of successes. We only know that in the first 6 successes, first 6 trials, there must be at least one success. So it is 1 minus the probability that there is no success in the first 6 trials, which is 1 minus 6 choose 0, 1 over 6 powered by 0, 5 over 6 powered by 6. And because y having binomial distribution means that the probability that y is equal to k is 6 choose k times 1 over 6 powered by k times 5 over 6 powered by 6 minus k for k 0, 1, and so on till 6. So in our case, we care about the probability that y is equal to 0. And it is nothing than 1 minus 5 over 6 powered by 6. The same result as we have here. And in fact, both of these approaches make sense, because what does it mean that there are at most 5 failures in the first success? It is in fact 1 minus the probability that all 6 trials, the first 6 trials, were not successful. So in fact it is 1 minus the probability of complementary event. So everything is connected with everything, as I would say, and this was the last discrete distribution I wanted to show you today. So next time we will continue with continuous random variables, and these discrete random variables we will calculate on the exercise this and next week. And so this is everything for today's lecture. Thank you for your attention.